Historically, audio machine learning has siloed sound into strict categories. Processing human speech, ambient noise, and music required completely separate specialized models. Attempting to train a single model on all these audio types simultaneously creates chaos. When speech transcripts, music tags, and sound classifications are mixed indiscriminately, the conflicting data formats degrade the model's ability to learn. This failure is caused by one-to-many interference. Datasets for speech translation have highly structured labels, while datasets for ambient noise rely on unstructured captions. Feeding these radically different annotation granularities into a large language model creates conflicting gradient updates during training. Qwen Audio addresses this through a unified 7 billion parameter multimodal model that processes over 30 distinct audio tasks through a single frozen encoder. We will examine how Qwen Audio relies on a strict hierarchical tagging framework and word-level timestamping to mitigate dataset interference. Then, we will look at how the Qwen Audio agent runtime uses this architecture to run a local asynchronous voice assistant. Resolving audio-language interference is the required first step to transition from static, text-based responders to real-time, context-aware digital agents that actually listen. The system initializes by pairing a frozen 640 million parameter Whisper Large V2 audio encoder with 7.7 billion parameter Qwen 7B language model decoder. Before encoding, raw audio is strictly preprocessed. It is resampled to a 16 kHz frequency, then sliced into 25 millisecond windows with a 10 millisecond overlapping hop size. This image shows an 80-channel MEL spectrogram, which mathematically maps temporal human hearing patterns. The preprocessed audio windows are transformed into this dense visual representation of frequencies. The data is then compressed using a pooling layer with a stride of 2. This reduces the length of the audio representation so that each resulting frame strictly equals 40 milliseconds of raw audio. To connect this to the language model, a linear layer takes these compressed frames and linearly transforms them to match the exact dimensional space of the Qwen 7B embeddings. Through this specific preprocessing pipeline, a text-native transformer can read complex, overlapping sound frequencies simply as another sequence of mathematical tokens. Returning to the dataset problem, feeding unstructured audio captions directly alongside highly structured speech translations creates those conflicting gradient updates. Qwen Audio fixes this by forcing the language model decoder to condition its outputs on a rigid sequential syntax called hierarchical tags. This diagram shows the multitask training format framework from the research paper. To begin the tagging sequence, the model must first define the broad category of the audio input. It is forced to route the input by predicting either a start of transcripts or start of analysis tag. The model then sequentially outputs the audio language tag, followed by a specific task tag, like translate, keyword, or question. This syntax forces collaborative knowledge transfer. Shared tags encourage the model to apply general audio understanding across similar datasets, while specific task tags isolate specialized knowledge, preventing datasets from interfering with one another. Structural dataset discipline via token conditioning enables multimodal performance across diverse tasks without catastrophic forgetting. Nearing the end of the tagging sequence is the timestamps tag. This tag triggers speech recognition with word-level timestamps, or SRWT. While a standard whisper model predicts timestamps at the sentence level, SRWT requires the model to interleave precise start and end time tokens for every single word. This chart shows the results of an ablation study comparing Qwen Audio trained with and without word-level timestamps. When SRWT is enabled, accuracy in audio question answering jumps from 0.56 to 0.579 on Clotho AQA and from 0.70 to 0.72 on Music AVQA. By requiring the model to predict precise start and end times for individual words, the training objective mathematically forces the model to tightly align the audio signal with specific temporal markers. This temporal grounding bleeds over into non-speech capabilities. The rigorous timing requirements for speech recognition improve the model's ability to localize and reason about abstract sounds, like machinery noise or music, across a timeline. Fine-grained timestamping functions as a core architectural mechanism that gives the language model a persistent, precise sense of time. Moving from base pre-training to enterprise deployment, updating all 7.7 billion parameters for a niche application, like custom wildlife acoustic analysis, is highly inefficient. The Qwen Audio fine-tuning pipeline relies on low-rank adaptation, or LoRa. Instead of altering the frozen base weights, LoRa trains tiny adapter matrices, preserving GPU memory while effectively teaching the model new acoustic patterns. Traditional audio pipelines rely on separate models, a speech-to-text module generating transcripts that are then fed into a separate language model. Qwen Audio handles both natively. This integrated architecture enables a specific inference advantage: continuous batching in production via engines like VLLM. Instead of waiting for the longest audio sequence, it dynamically packs uneven incoming requests into a dense block of GPU memory. This allows the engine to handle parallel requests at the token level, eliminating idle processing gaps and drastically improving GPU utilization. Achieving high throughput via continuous batching directly improves the unit economics of deploying multimodal models in production environments. To transform this multimodal model into an interactive assistant, developers use the open-source Qwen Audio Agent repository, which provides a dedicated runtime layer. In this full duplex logic flow, the top foreground layer handles rapid audio I/O, completely decoupled from heavy background reasoning. This enables true interruptibility. The runtime instantly severs the foreground audio stream when the user speaks, without delaying the background process. The runtime also integrates the Model Context Protocol, or MCP. This allows the agent to route complex requests, like writing and testing code, to a native backend agent such as OpenCode or OpenClaw. Once the background task completes, the system naturally pushes the result back into the active foreground conversation queue, alerting the user without breaking the flow of dialogue. Without an asynchronous, decoupled runtime, even the fastest multimodal models freeze during complex tool use, destroying the illusion of presence and breaking the conversational experience. The complete technical stack relies on Whisper-ML spectrograms, conditioned by hierarchical tags and word-level timestamping, inferred via continuous batching, and managed by a decoupled agent runtime. The model's performance across 30 distinct benchmarks suggests that structural dataset discipline, rather than simply increasing the parameter count, drives the improvement in audio understanding. Bypassing modular speech-to-text pipelines eliminates latency bottlenecks, enabling reasoning on pure acoustic data. The next generation of enterprise AI will move away from chat boxes and toward persistent, full-duplex voice agents integrated directly into local developer workflows and complex acoustic environments. Check the description for links to the Qwen Audio Archive paper, the GitHub Agent repository, and the Trellis Collab fine-tuning resources.